All right, so the total acceleration from this is just the same sort of thing we've been looking at, basically, right? So we've got, we're going around in a circle, right? So we've got some axes. One's pointing towards the center of the circle, one's pointing in the direction of motion. It's tangential and radial. And we've got some acceleration. Part of that is speeding up and slowing down, the tangential. And part of it is turning, the radial. Okay, so we've got an acceleration in general that's doing some of each, right? It's turning us a little bit and it's slowing us down or speeding us up a little bit. The total acceleration is the vector sum of these two effects. And you'll remember that that means that we use the Pythagorean theorem to figure out what that magnitude is, right? So how much total acceleration is in the system. Okay. So how does this look like on our circle, right? We've got our circle. We start off here with V1, right? And we end up at V2. What do these accelerations look like? So let's go to green. So when we're starting here, remember we had AR going this way. This will be for 1. And then we had an AT pulling us back. That'll also be for 1. And so our net acceleration is going to come back a little bit in our previous example. So I'm going to want to use the same example, basically. And how about over here? Well, when we were here, we had an AR, this for 2, and an AT, this time for 2. These would be the same if it's uniform. And then we have our A2 over here. So this was actually A1. So we have these two different directions of travel. And each one of these basically follows the same logic. A1 squared is equal to AR1 squared plus AR2 squared. And A2 squared is equal to AR2 squared plus AT1, AT2 squared. So these are changing. If there's a tangential acceleration, this changes, even if this is tangential is constant, because remember, AR is proportional to V squared over R. So the acceleration is the tangential acceleration is changing the speed, therefore it's changing the radial acceleration, therefore it's changing the total acceleration. Okay. All right, so this does not mean that this acceleration doesn't have the same components. So we already talked about the acceleration was broken up into both y and z components. So it can be broken up into y and or x and y components too. So that this same acceleration here we can break up into a y and down here a x. So that might help us with what we're doing. So the physics and the coordinate system don't always match up perfectly, right? The physics, we care about the turning, we care about the speeding up and the slowing down. And for the kinematics, for the math part, sometimes we care about just what are the positions on the field that the thing is at. And these are the things that will change the x and y components, whereas these things tell us more about what physically is happening to the person relative to that person's perspective. So that same acceleration has two different pairs, it actually has an infinite number of pairs, but has two different pairs of numbers that constitute the vector that are equally interesting, that are interesting in different places. So I'll finish up by calculating A for you once as our example, and then we'll be done for the week. Bye now.